All right, so we're ready to discuss what's called Green's theorem. And we're going to give two different versions of Green's theorem. And Green's theorem, basically what it does is it connects the two different ways, first of all, that we talked about rotation in a vector field by looking at a circulation integral and then later at the curl of the vector field. And then in the second case, it relates the ideas of kind of a spreading out in a vector field. So looking at flux integrals and divergence in the vector field. So let's jump in, and the first thing we want to talk about is rotation in a vector field. And we'll say that our vector field is given by f, and it has the coordinate functions p and q. And so Green's theorem is a theorem about vector fields in the plane. So for this entire topic here, we're only going to deal with vector fields in 2 dimensions. Okay, cool. So let's go ahead and draw a sample vector field. And I'm not going to really assume anything about this vector field. I'm not going to assume that it's conservative. I'm not going to assume that it has the path independence property. I'm just going to assume that it's just a collection of arrows. At every point in the plane, I have an arrow. There's my vector field, not assuming anything about it, except that it's defined all over my plane here. Okay, and now let's suppose that we have a curve that will be simple, and it will be closed, so it forms a loop, and we'll give it a positive orientation, just to stick with our convention of positively oriented curves. And so recall that we had a way to measure the rotation in the vector field around this curve, which I'll call C. And that was the circulation integral. So the circulation integral of this vector field over this closed simple curve, positively oriented curve C, was just the line integral. But we gave it some fancy notation with the circle around the integral. Okay, so we're just really more or less measuring the component of the vector field, or how much of the vector field sort of lies around this curve. So we're just adding up sort of the vector field as it goes around this curve. So if the circulation integral is a big number, then there's a lot of rotation around this curve. Okay, so that's one way to kind of measure the rotation in the vector field. But we also had another way that we mentioned really briefly in connection with conservative vector fields, and that was the curl. So the curl of f, recall, now it's really a cross product, and it's denoted using this del operator. And what it basically is, in 2 dimensions, I can state it pretty easily. It's just, well, technically it's a vector. But what I'm going to do is, because in 2 variables, there's only going to be a z component of the curl, I'm just going to write that the curl is actually qx minus py. Okay, so if I set up the cross product, I would just have so my component functions would be p, q, and then 0 for the z component, and you would just work it out. And the curl of a 2-variable vector field, or a vector field in the plane, turns out to just be the partial of the y-coordinate with respect to x, and then minus the partial of the x-coordinate with respect to y. And so what does the curl tell me about my vector field f? Well, at every point where the vector field is defined, the curl basically tells me how much of the vector field is rotating around that point on a very, very small scale. So the curl is more or less just measuring the rotation at individual points again, at a very, very small scale. So at this point, it's just measuring how much rotation there is in the vector field, in here, in here, in here. And what I can do is I can say, okay, well, let's look at the curl over the region that's bounded by the curve C. So this closed simple curve encloses a region that we'll call R. And what I can do is this quantity here, qx minus py, is measuring the rotation at every point in this region R. So what I can do is I can actually add up the curl. So I can do a double integral over the region, and I can add up all the little bits and pieces of rotation in there over small pieces of area. So in this little piece, I have so much rotation. In this little piece, I have so much rotation. And if I add up all of the rotation over all the points, then it's not surprising that that's going to be connected to actually the circulation line integral. And in fact, they're going to be equal. So what Green's theorem says, and now this is Green's theorem, maybe you can say part 1. So this is Green's theorem for circulation. And if you look in books, most of the time when they refer to Green's theorem, they're referring to this version of Green's theorem, the circulation version. And so what it says is that the circulation integral of the vector field, so basically the amount of rotation on the boundary of the region, is equal to the double integral of the curl over the region bounded by the curve C. Which is really cool. And you should think about this sort of like a higher dimensional analog of the fundamental theorem of calculus. And what I mean by that is, remember, the fundamental theorem of calculus in one variable basically says that if I integrate a function, I try to find the area underneath the curve, somehow, if the function has an antiderivative, the area only depends on the value of the antiderivative on the boundary or on the endpoints of the interval. And that's basically what this is saying. It's saying that if I want the curl or add up all the contributions of the rotation inside the region, all I really need to do is add up the contribution that I can measure on the boundary of the region. So it's relating something on the interior of the region to the boundary of the region, just like in the one variable case. So this is what Green's theorem says for circulation. And so it's really awesome because we've already seen that sometimes line integrals, like if you're integrating over a square, you may have to do a lot of different line integrals to get the circulation integral. But this is going to relate it back to just a simple area integral of just a function that we can compute. So it's going to be extremely helpful. Okay, so now that we've talked about the circulation version of Green's theorem, basically relating the curl or the rotation inside the region to the circulation on the boundary, let's talk about the flux version of Green's theorem. And now what this is really going to relate is not rotation, but sort of the spreading out. I'm just going to put this in quotes because this is just kind of how I think about it. But we're going to talk about the spreading out of a vector field. F, and we'll use the same notation. So F has the component functions P and Q. And again, we want F to be a vector field in the plane. And so there's kind of this dichotomy between, well, rotation in a vector field and then kind of spreading out or dispersion of a vector field. And so we had one way to measure that. So again, just like with rotation, let me draw kind of a sample vector field. And I'm not going to assume anything about the vector field. I'm just going to assume that the vector field consists of arrows. It might be conservative. It might not. I don't know. Here it is, though. My random vector field. And I have a simple, closed, positively oriented curve, which I'll call C. And I'll give it my positive orientation, just so all of our kind of conventional notation is going to fit together. Great. Okay, so recall that we had this notion of a flux. So a flux integral. Now what we meant by that, well, later we're going to have another idea of flux, but here specifically we mean the flux out of the curve. And what that is basically measuring how much of the vector field passes out of our curve C. And so the way to think about this is I just measure at each little piece of the curve how much of the vector field is passing out of the curve, or how much of the vector field lies in the normal direction of the curve. Okay, so the flux integral is just, well, it's a line integral over this closed loop, and I project at each little piece of the curve the force field or the vector field instead of the tangential direction, the normal direction, and have my ds, little piece of the curve. Cool. And so what this is really measuring is measuring how much of the vector field is spreading out, so that's why I use this term, spreading out, across the boundary of the curve. Cool. So just like with rotation, we had this idea of curl of a vector field that sort of said the rotation measured the rotation at a point. With spreading out, we have this idea of divergence of f. And what the divergence is it's written like this, so again using this del operator of f. So if you remember what the del operator is, it's just the partial with respect to x, then partial with respect to y. So what this ends up being is partial with respect to x of p plus partial with respect to y of q. Okay. So then what does this kind of represent geometrically? Well, if I evaluate the divergence of the vector field at a point, just like the curl represented the rotation around the point, the divergence is basically measuring the spreading out or the divergence of the vector field around that point. So, you can think about how much of the field is moving away from that point. And over here at this point, we can sort of measure or quantify at that point using the divergence how much of the vector field is spreading out away from that point. Cool. So what we can do is something very similar to what we did with the curl, is I can add up, if I call this region enclosed by the curve C, the area region R, I can add up all the little contribution of the divergence. And I can do that as a double integral over the region. So I'm just adding up the divergence. Px plus qy over all of these little area regions contained in my region R. Okay, and you can probably guess the conclusion. So the second version of Green's theorem, which is Green's theorem for flux integrals, says that, well, again, it's relating something going on the interior of the region. So the spreading out on the interior, not surprisingly, is equal to the spreading out on the boundary. So the flux integral equals the sum, or the double integral, over the region enclosed by C of the divergence. So again, this is a really cool theorem because it's going to allow us to, when we're computing a flux over a boundary, we can convert it to a single double integral, and we have a lot of practice dealing with double integrals. And in general, a double integral will be easier than a line integral. But now what we're going to see, and maybe what's even more interesting, is that there are examples of double integrals that are difficult, but when we convert to a line integral, they'll actually be pretty simple. Okay, so now I just want to kind of give an overview of what we just said, because these two versions of Green's theorem, if we understand them now in the plane, as they're stated in the plane, what we're going to do later when we go up to three-dimensional space is going to be more or less crystal clear. So let's think about this. So we have the circulation version of Green's theorem that says, okay, the integral over a closed curve of the circulation integral, so the force along the tangential direction of the curve, equals the contribution over the entire region enclosed by C of the curl. So that was Qx minus Py. And so recall that our vector field F, P and Q are the component functions. Okay, and then the flux integral, similar. So we take the flux integral, or the flux version of Green's theorem, but now we're taking this kind of the spread across the boundary, so the component of the force lying in the component of the vector field lying in the normal direction, and that's equal to just adding up the spread at each individual point, so the divergence. So that's Px plus Qy. Okay, so notice something right away. So we talked about conservative vector fields. So recall that if the curl of a vector field is 0, and remember that in the plane that means these two things are equal, well then the right-hand side of this circulation version of Green's theorem is going to be 0. So if the curl is 0, you see that over every closed curve, my circulation integral will be 0. Same thing for flux. If I have a divergence-less vector field, so if the divergence of my vector field is 0 everywhere, then all of my flux integrals are going to be 0. So you can just read off some really nice information from these theorems. And also, like I said, these theorems are generalizing the fundamental theorem of calculus to higher dimensions. This left-hand side in both cases are either measuring spreading out or rotation on the boundary, and we're basically saying that that's the same thing as spreading up, as adding up the spreading or rotation at each individual point. So the contribution over the area region is equaling the contribution on the boundary. And that kind of makes sense. However much water is spreading out over a region is going to equal the water that spreads out over the boundary. And the amount of rotation in the water inside the region sort of gives rise to the region over the boundary. So they're really cool theorems. It's really worth thinking about what they're saying. And it's, sort of important to relate back to what we said before about if we have a curlless. So let's just write that down. So curl equals 0 means no circulation. So all of my circulation integrals will be 0. And if divergence is 0, this is just kind of a good colloquial way to think about it. If divergence is 0, then we have no flux. So again, it's this cool dichotomy between curl and divergence, circulation and flux. And you can think about this with water. I mean, what's going on with water? The water, of course, could be still, but if there's any motion in the water, it's either divergence away from a source. Divergence, you can also think about negative divergence being convergence, so kind of moving in towards a sink. But then the other thing it can have is rotation, so curl or circulation. So it's really just giving a mathematical description of what we can see going on in vector fields. So in the examples, we'll see a lot of cases where we're trying to find a line integral along the boundary of a region. And it's going to be difficult, so what we're going to do is convert it to an area integral, double integral, of either the flux, either of the curl or the divergence. And so that's one way to apply Green's theorem. And as we've seen, line integrals can be a little bit tricky, but double integrals, maybe we have a little bit better handle on. But there is some examples that go the other way. So there are some examples of where we have a double integral. So specifically, what I want to talk about is if I want to find the area of a region R, and let's say that R has a boundary curve C, so if I want the area of a region R bounded by the curve C, well, of course I can just take the double integral of the function 1. I just add up all the area elements, and that'll give me the area of R. But maybe that's difficult. I mean, sometimes double integrals are a little bit tricky, particularly when maybe they're hard to describe. So we'll see examples for, say, ellipses or other kind of regions bounded by parameterized curves where it's just really hard to just compute the double integral directly. But here's the trick. Okay, so what I'm going to do is I'm just going to introduce a vector field that I'm going to say is negative y in the x direction and x in the y direction. And here's what I'm going to do. I'm going to do something kind of tricky. I'm going to say that this is 1/2 the double integral over R of partial x of the function x minus partial y of the function minus y. Of course, dA. And so notice that, well, this is true. I mean, what happens here? I just get 1 minus 1, so 2, and then the 1/2 cancels the 2, so these are really equal. But notice that this is actually the double integral of, if I call this P and this Q, then this is Q x minus P y. And now I can actually apply Green's theorem, so specifically the circulation version of Green's theorem, in reverse, and I can actually write this as a line integral. or a circulation integral, over the boundary of the region of R. So of F, which recall is this special vector field that I'm sort of using as an auxiliary object, but actually computing this line integral over the boundary of the region, I want the area. So I can actually express the area of a region as a line integral over its boundary. And that is super cool, because if you think about it, I could just have some arbitrary region, but if I can sort of better describe the boundary, all I have to do is just do this line integral over the boundary. And there's actually some really interesting applications of this principle. There are actually devices that allow you to trace out arbitrary regions, so the boundaries of arbitrary closed regions, and they'll actually measure the area just based on how the object or the instrument traces out the region. And these have a really rich history. And so maybe you can go read about that a little bit. But this application of Green's theorem is really cool to find areas of regions in this way. And again, it's just going back to the idea of relating sort of the interior of regions to the boundary. And there's this kind of intimate connection between the interior and the boundary, derivatives, integrals, all this stuff, fundamental theorem of calculus. That's really what we're hitting at here. Okay, so here's a good example. So we want to evaluate this circulation integral over this vector field. And the curve is this triangle with vertices 0, 0. So let me just go ahead and sketch out what this triangle looks like. So one of the vertices is on the origin, and then one is out here at 2, 2, and then one is at 0, 2. And we have a counterclockwise orientation. So here is our curve, C. Okay, and now this is actually very doable. I mean, we could break this up into 1, 2, 3 line integrals and just add up sort of the contribution along each one, and that would give us the total circulation, but it would require doing 3 integrals. Okay. But let's see what happens when we apply Green's theorem. So here's our curve C. Notice that because this is a closed simple curve, it actually encloses a region that we'll call R. Okay, and so here's 1, 2, there's 2, just a label. Great. Okay. So what does Green's theorem say? The circulation version. It says that, okay, I want to find this circulation integral. And, you know, I could parameterize the curve, etc., etc. So that's one big bonus. I'm not going to have to parameterize the curve if I use Green's theorem. So what this is equal to is the double integral over the region of, so basically the curl, or really the z component of the curl of this vector field. So q x minus p y. And that's over area elements. Okay, but let's just see what this integrand is. So this is p, and this is q. So qx is going to be 2xy, and py is going to be x over y. So what I really want is the double integral over this region of what? Let's see. Of 2xy minus x over y dA. And this region is just a triangular region. So, I can fix a y between 0 and 2. Write this as integral from 0 to 2 of y. And then where does x go? X goes from a fixed y, 0 up to that y value. And then 2xy minus x over y. And this is going to be dx dy. Okay, and then we can evaluate this. So it's the integral from 0 to 2 of, okay, this is going to become just x squared y, it looks like. And then evaluated from, let's see, just at y, basically. So yeah, that's x squared y. So that's just going to be y cubed, it looks like. And then what is this going to be? Well, it's going to be x squared over 2 evaluated, so y squared over 2y, or in other words, y over 2. Y over 2 dy. Okay, so let's see, what do we get? We have y to the 4th over 4 minus y squared over 4 evaluated from 0 to 2. But what is this? Let's see, 2 to the 4th is 16 over 4, which is going to be 4. And then 4 over 4 is 1. So it looks like our final answer is 3. And that's the same thing that we would get if we broke this up into 3 line integrals going around the boundary. But we're getting around that by just integrating over the curl, or the rotation within. So the rotation inside is this integral. The line integral is the rotation along the boundary. They're the same. They're both equal to 3. Okay, so this is a very similar question, but instead of finding the circulation integral, we want to find the flux integral. And so we have this square, and we could actually just break up the square into its 4 sides. So here, 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 and it has a counterclockwise orientation, so it looks like this. And what we could find is we could find the flux across each one of the boundaries and add them up, but we would have to do 4 integrals. And that sounds like a big pain. So it's going to be better to just convert it into a single double integral over this region. And what's even better is this region. So we have the curve C, we have the region enclosed, which we'll call R. The region is very easy to describe. So what does Green's theorem tells us? It tells us that the flux integral, so adding up along the boundary all the components of the vector field that's going outside the boundary, or the component in the normal direction, is equal to the double integral over the enclosed region of the divergence, basically how much the field is spreading around each point. So that's going to be px plus qy, where again, this is going to be p, this is going to be q. What is px? It's going to be cosine squared y. And then what is qy? That's going to be sine squared x. Okay? So then what is this equal to? It's equal to the double integral over this region of cosine squared y plus sine squared x dA. Okay, and so x and y both just go from 1 to 2, so we have 1 to 2, integral of 1 to 2, of what now? Let's see. So what can we do here? So unfortunately, you might be tempted to say, oh, cosine squared y plus sine squared x is 1. But remember, that's only true if the arguments are the same. And they're not here. So we're actually going to have to evaluate these integrals. So we have cosine squared y plus sine squared x. And this will just be dx dy. It's not going to matter which order I integrate, since it's over a rectangle. Okay, so what's the antiderivative of sine squared of x with respect to x? Well, here's where we're going to want to use our formulas, our trig identities. This is going to be 1 minus cosine 2x, all divided by 2. And cosine squared is going to be, well, this is really cosine squared of y, is going to be 1 plus cosine 2y, all over 2. Okay, so then what's an antiderivative of sine squared x? Well, I just need to take an antiderivative of this. So we have x, and then this is, what is this going to be? This is just going to be minus cosine 2x over 2, but I can just write that as over 4 and put a 2 there. So this is the antiderivative of that. And the antiderivative of this guy is going to be 2y, so very similar, cosine 2y over 4. And then I just want to evaluate this antiderivative from 1 to 2. So that's going to be, this is just going to be 1 when I evaluate x. So that's going to be 2, and then minus, so I'll have cosine of 4, and then minus minus, so plus cosine of 2, so minus cosine of 4 plus cosine of 2 all over 4. And then plus, well, same thing here. I'll just have a 2 when I evaluate y from 1 to 2. And now I'll have plus cosine of 4 minus cosine of 2 all over 4. Okay, and so what happens here? Well, notice that these have opposite signs. So it looks like the cosine 4s will cancel, the cosine 2s will cancel. We'll have 2 over 4 plus 2 over 4. So it looks like our final answer will be 1, just like that. And I prefer doing that than actually breaking this up into 4 line integrals and doing it and having to parameterize the curves. This is a walk in the park. So Green's theorem, as you can see, is very powerful. It's very useful. So the last 2 examples took a line integral, either a circulation integral or a flux integral, and made it simpler by converting it to a double integral. Okay, but there are actually examples where there are double integrals that are easier to evaluate if you convert them to a line integral or a circulation integral. And that's going to be the case here. So we want to find the area bounded by this curve, parameterized by this vector value function. And so I recommend that you actually plot this yourself. But what this curve looks like is it's sort of like a balloon, kind of like that. So it's a little bit hard to describe. So if you tried to do, even if you try to use polar coordinates or something like that, it's not even clear what this is. It's not y is not a function of x here. It doesn't really even look like a polar function. So it looks a little bit difficult. Okay, but there's the curve. It's parameterized here. And the inside region, which we call R, that's what we want the area of. So recall that we had this nice way to kind of mix and match, and what we do is we introduce this kind of auxiliary vector valued function minus yx, and what we're able to do is say that the area of the region is really 1/2 the integral over the boundary, so the circulation integral, of this particular vector field minus yx dot with the unit tangent direction. Okay, so let's see what happens when we plug all that in. So remember that we're going to do a line integral, so we need the parameterization. We're going to need to take the derivative. So the derivative is 2 cosine 2t cosine t. Okay, and so this is going to be 1/2, and then we have the integral from 0 to pi. So we already have the parameterization of the curve, which is great. And then minus y is going to be, so minus y is minus sine t, and then we dot with the x component of the derivative, so this is going to be minus 2 sine t cosine of 2t plus x, which is sine 2t, dot with the y component, so we'll have cosine t sine 2t dt. Okay, and so this integral isn't super easy to do, but it's certainly easier than the alternative. And we can do this. Okay, so you can either just plug this in our computer, or I'll show you how to do it without. The thing to notice is, well, the cosine 2t and the sine 2t, I don't really like that. Okay, and so what I want to do is I actually want to convert those back to just sine of t and cosine t. So recall that cosine of 2t is cosine squared t minus sine squared t. So this is 1/2 0 to pi, and then we'll have minus 2 sine t, and then we have cosine squared t minus sine squared t, and then we have plus sine 2t is 2 sine t cosine t, so this is 2 cosine squared t sine t. Super cool. Okay, dt. Now look what happens here. So the minus 2 sine t times cosine squared t plus 2 cosine squared t sine t will cancel. And what we're left with is actually 1/2 integral from 0 to pi of 2 sine cubed t. And it's even better than that because the 1/2 cancels with the 2, and I just want to integrate 0 to pi sine cubed t. And this is one of our classic u substitutions, so we actually want to let u be cosine t, so that minus du will be sine t dt, du dt. And then what do we get? Well, we're going to get, so one of the sine t's gets absorbed with the dt, and we get a minus du, so we're going to get a minus, and then let's see if cosine is let's see, if t is 0, cosine of 0 is 1, and then cosine of pi is -1. And then we're left with the sine squared, but that's 1 minus cosine squared, which is 1 minus u squared du. And so we can flip these up, so that's -1 to 1. We'll have 1 minus u squared du. And this is u minus u cubed over 3, evaluated from -1 to 1. Okay, u evaluated from 1 to -1 is just going to be 2. And then we'll have minus, this is going to be, u cubed, that's going to be 1, and then -1, so minus 2/3. So that's 6/3 minus 2/3, which is 4/3. So that's the area of this crazy region. And we did it without really being able to describe the region at all. All we knew was this parameterization of the surface. So again, you're starting to get a glimpse of how cool Green's theorem is. We're able to find areas of regions just by integrating along the boundary, this kind of special vector field. So it's really cool stuff. So this is my favorite application of Green's theorem, and it's so classic. So you have an ellipse, and now I'm sure you know the equation for the area of a circle, but maybe you have this memorized or not, but a lot of people don't really know the area of an ellipse. So recall that an ellipse looks something like this, just a stretched out circle. And now, based on this equation, y is going to be going from b to minus b, like that. And then x will be going from minus a to a. So you can think about an ellipse as just a circle that has a different radius in the x direction than in the y direction. And so it actually sort of makes sense, the equation. So when a equals b, you just get pi r squared because the radii are the same. But if the x radius is a little bit longer, if it's stretched out in the x direction, well then you just multiply by however far you go away from the center in the x, and then however far away you go in the center in the y. So it's a very logical kind of generalization of the area of a circle. But let's see where it comes from. Okay, so of course a and b are positive numbers. That goes without saying, but let's just say it. Doesn't hurt to say it. Okay, so it'll be positive numbers. Okay, and here's what we're going to do. Well, the area we know is the double integral. So here is my region R inside here. But I also know that I have this boundary curve C. Okay, so the area of R, we actually have a way to relate the area of R to a line integral along the boundary curve C. So it's equal to 1/2 the line integral of the curve. And then remember this really special vector field minus yx, and that's the vector field we're going to integrate. Okay, so that's what the area of an ellipse is. But of course, I'm not done. I need to actually parameterize the curve. So recall that it's not so hard to parameterize an ellipse. It's very similar to the parameterization of a circle, but I just want to specify my x radius, if you will, so a cosine t, and then my y radius, b sine t. And here t will go, just like for a circle, between 0 and 2 pi. Okay, and we'll need the derivative to set up our line integral. So this will be minus a sine t, and then b cosine t. All right, so we're ready to plug everything in. So the area is just this line integral, so 1/2. And then we're integrating from 0 to 2 pi of what? Okay, so we have minus y, so it's minus b sine t, dot with x prime of t here, so that's minus b sine t, and then dot with minus a sine t, so that's b times a sine squared t. And then we have x, which is a cosine t, dot with, well, the derivative of y, so y prime of t, which is b cosine t. So we get plus b a cosine squared t. Okay, but look how cool this is. So this is the integral from 0 to 2 pi. Sine squared plus cosine squared is 1, so what are we left with? ba, or a times b. All right, but then we're done. This is just 1/2 times 2 pi times a times b, which we can so the 1/2 cancels with the 2. What are we left with? Pi a b as the area of an ellipse. That's the easiest way I know to derive the equation for the area of an ellipse. But of course, it requires, sort of a pretty deep theorem in calculus, Green's theorem. But again, I mean, you're just seeing how cool Green's theorem is, what it's able to do. Not only are you able to take difficult line integrals and convert them into simpler area integrals, you're actually able to just express the area of regions by line integrals. So it's just super cool. Hope you're appreciating it.